Alright, so by request I'm going to go through a power transmission question. So what I'll do is I'll just draw a typical sort of transmission question setup, and we'll walk through how to figure out what the current and voltage is at different points. So the first thing we're going to start off with is a generator. Okay, so this will be our generator down here. And that generator is going to be connected to a step-up transformer. Now just notice that when you draw your transformer, because a lot of exam questions will actually ask you to draw these circuits, notice that the sides of the transformer are not connected to each other. Right? So the transformer works entirely off of electromagnetic induction, so that means that the either side is not connected. So make sure that you're drawing complete circuits on either side of the transformer. And we've got these wires here, and they're going to be connected to a step-down transformer. And on the other side of the step-down transformer, we'll have some sort of load of some sort. So I'll represent that with just some load. Could be a resistor. If it was a model circuit, in real life it could be a house or a building or something like that. Now, we'll say that this step-up transformer, we'll say that it's a 1 to 10 ratio, so that means that there's 10 times as many turns in the secondary coil as the primary, and we'll say that it's the opposite on the other side. It'll be a 10 to 1 for a step-down transformer, so that means that there's 10 times more turns in the primary than the secondary. Now, in terms of the generator, let's say that we know some information. Let's say we've got 100 volts RMS, and in terms of current, we'll say that we've got maybe 5 amps RMS. So if you had a question where the RMS values were not given, let's say that they gave you the peak values instead, you need to divide those by square root of 2 to find your RMS values. So anytime you're doing any calculations, you need to use your RMS values. So just keep that in mind. Now, that means that the power that's going to be produced by this generator is going to be I times V. So this is I, this is V. When I multiply them, it's going to be 500, and it's going to be in watts. So that's the power that's being produced by this generator. Alright, so now what we're going to do is we're going to track how the current and voltage change as we sort of go towards the load on the right side. The first thing that we need to know what the resistance of the wires is. We'll assume that because these wires are so short on either side, we'll assume that the resistance is negligible. But we'll assume that these wires here, which are longer, will have a resistance that is not negligible and maybe is equal to 10 ohms. Okay, so the first thing I'm going to start off with is my voltage. So we know that we're getting 100 volts RMS. That's going to be in the primary side of the transformer, this step-up transformer. Now on the secondary side, that voltage is going to get stepped up by a factor of 10. So that means that it's now going, well, 100 times 10, it's going to be 1,000 volts RMS in the secondary coil. So I encourage you to, when you're doing these questions, to actually just write these things down on the diagram. It's a lot easier. Now, we'll also do the same with the current. So our current in the primary is 5 amps, but remember that the current is actually going to get stepped down by a factor of 10. So it's going to get stepped down to 0.5 amps RMS. And because we're assuming that our transformer is ideal, that means that the power in both coils should be the same. So we've got a power on the left side is 500 watts, but on the right side it would still be 500 watts. So again, we're assuming that the transformer is ideal. In real life, of course, it wouldn't be ideal. You get eddy currents and this sort of thing. You'd actually lose power within the transformer. But in this case, we'll assume that, because in physics year 12, we assume that the transformers are ideal. Now, there's actually going to be a voltage drop in these lines because there's a resistance. So the voltage drop is going to be given by Ohm's law, which is V equals IR. That's going to be my voltage drop. So the current in the lines, that's not going to change. That's going to be 0.5 amps. And my resistance is also not going to change. That's going to be 10 ohms. So that means that my voltage drop is going to be 0.5 times 10, which is going to be 5 volts. So we're starting off with 1,000 volts RMS, but then through the course of passing through these lines, we're going to lose 5 volts of that, which is going to then bring the total to 995 volts RMS at the far side here, which is what it's going to be in the primary coil of that step-down transformer. Now what's going to happen is we're going to get that voltage step down by a factor of 10. And so that means on the secondary side, it's going to be 99.5 volts RMS, and that's what the load is going to receive as well. Again, we're assuming there's no resistance in these wires. We're assuming that the transformer is ideal. So that's what's going to happen there. Now the current is going to be 0.5 amps throughout this entire part of the circuit, and it's actually going to get stepped up by a factor of 10. So that means on this side it's going to go back up to 5 amps RMS. So this setup actually illustrates the purpose behind our step up and step down transformers, because you start off with 500 watts at the generator. Now to figure out, well, how much power is actually being delivered to this load here, well, P equals IV, so it's going to be 99.5 times 5, and that works out to 497.5 watts. So power on this side is 497.5 watts. So a very small power loss of only 2.5 watts. Now if we didn't have the step up and step down transformers, what we would end up having is that we'd still have our 100 volts RMS on the left side. So just try to picture this without the transformers. We'd have 100 volts. We'd still have a 5 volt drop in the wires, which means that over here we'd end up with 95 volts, and we would multiply that by a current of 5 amps, and we would see that is 475, I'm not sure if you can see the screen there, but it'd be 475 watts. So we'd have a bigger power loss. Now because the current and voltage is relatively small, the difference between the two is not amazing. I mean 497.5 versus 475, but as the currents and the voltages increase, then the difference between the two will also increase as well. So this is a way that was designed to reduce the amount of power loss and make power transmission more efficient. So most of the questions involving power transmission will involve something with this. They might give you the values on the right side and you have to then work it back towards the left. They might give you values on the left side and you work it the way that we did in this question. So you just have to figure out which information is given. I strongly encourage you to use the diagram, write on the diagram what the current and voltage is at each point. So remember, is it a step up or is it a step down transformer? Multiply it by the correct ratio to figure out what it is on the other side. And the one thing is, don't forget about that voltage drop in the wires. That's the most common thing that students forget. Another common misconception is that students will calculate this voltage and in fact forget that it's actually the voltage drop. So it's not the voltage that's going into this side of the transformer. This is actually just the voltage drop from the beginning at this coil to the end at this coil. So that's your voltage drop. So once you know what your voltage is coming in, subtract that off and you get your voltage that's going out into that transformer there. So hopefully that sort of clarifies things a little bit.